Okay. Good evening, everyone. Welcome to week 3 of the problem solving sessions for the course Linear Algebra through Geometry. My name is Bhavideep Rai. I'm a PhD in IIT Madras. Okay. And uh, let's begin the course with begin the week with this week's discussion. By the way, I looked into the assignments of week 1 and week. So um, I did not. Okay, sure. Uh, what was I saying? Oh yeah. So I looked into assignments. I doubt the problem itself just thing the answer. But so I decided not to discuss assignment questions here. Okay. But if you want to me to discuss, just let me know. If you have a particular question that was a bit confusing, okay, just let me know. All right. Um, is that fine, or should I with this week's content? Oh, is it so? Okay, just one moment. I'll switch off the fan and see.
Uh, yes, it's fine. But then your voice is not clearly
Yeah,
audible. It's
it's
breaking in
breaking.
between. I don't know whether
Is
this
it
is with
still
everybody
breaking? Can you hear
or
me?
only.
No,
Yeah.
it's fine. Okay, switched off the fan. If it's still breaking, then I'll turn off my video. Okay, just let me know. Great. Okay.
Yeah,
Satinder
it's
is also
breaking.
here. Hi, Satinder. We have just started.
Yeah,
Yeah,
now
so
it's fine.
Satinder, I was just saying that the assignment 1 and 2 questions, I think they are quite straightforward, so I'm not going to discuss them. Maybe the following assignments, I'll discuss the questions. Okay. But let me know if you still want me to discuss the assignment 1 and 2 questions. Okay. Else, I'll just begin with this week's content. Just let me know. Um, okay. So what is this week's content? This week's we introduce vectors. Okay, and we'll solve some simple questions on vectors. Okay, I just want to do like a quick recap of what we did in vectors. First, okay, we saw what vectors are. Okay, and we saw what say something like norm is. Okay, the vector norm or the Euclidean norm is. Okay, and we looked at dot product of vectors, angle, computing angle between two vectors, linear dependence, independence. Okay, and well, what else did we see? Unit vectors and orthogonality or orthogonal vectors. Okay, so I just want to tell the following thing that um, I was telling that there are these two major views in linear algebra, and to view a matrix. Okay, one view is the row view as a system of equations. The other view is the column. The column view is a collection of vectors. Now, what are vectors? Are column mates. These are column. If rows, you were saying these represent coefficients of the system of the equations, whereas column view, we say these are vectors. Okay, but this is the, vectors are just column matrices, but how do we, what is it graphically? What is it geometrically? Okay, I was telling you that they are points in space because, we can take these as coordinates, but they are slightly more than points. Okay, points are very static objects. Okay, and vectors actually do not have a location. What I mean by that is a vector is a combination of two things. Okay, vector is a combination of two things. One thing is the direction, and the other thing is the magnitude or length. Okay, vector is represents a direction plus a magnitude, so it is not actually representing a point in space. What it is telling you is, okay, what philosophically vector is telling you is, it is telling you, it is talking about movement across space and movement in a straight line, which is also called displacement, right? Okay, so we always look at it with respect to the origin. Okay, of course, like I think Satyendra had last time asked about origin, we can move about the origin and so on. Now, thing about vector is if I have, let's say, a vector 3, 4, okay, and this is my graph plot, okay. Then 3, 4, if you plot it as a point, okay, so it'll be 3 on the x-axis, okay, and 4 on the y-axis. So this point, right? So if you plot it as a point, then it'll be like this. But what actually 3, 4 as a vector means, not as a point means, you take a line from the origin, you take an arrow pointing to 3, 4. What it represents is a direction, okay, is a direction wherever it's pointing, and a certain length, right? And what if you say, okay, if I don't want the vector to be starting from the origin, it may start somewhere else. It's okay. You can do that. You can make the vector start here. The vector is unaffected by this. Any kind of vector operation, okay, is such that as long as the direction and the length is respected, it's not a problem. You can even place it here. What does it tell you? These lines need to be parallel. Okay, these so that's why vectors are very useful in physics, because these represent naturally it represents the concept of forces. Okay, I mean during high school physics you may have seen that if I have this kind of block body diagram, and a force is coming from here, a force of 10 Newton is applied on the block. Okay. Oh no. Okay. I'll turn off my camera. Okay. Okay. Can you hear me now? Is it clearer, Kishore? Hello? Okay, okay. I've turned off my camera. Probably my internet is bad. There is uh, internet issue in the department, uh, some repair going on, probably because of that. This is happening. But it's okay. So where was I? Okay, yeah. So a force of 10 Newton is applied on the block. That's what we used to say. The force was being applied here, right? Actually, if you think about it. But when you make that block body diagram, or what it used to be called, okay, I mean, if as far as I recall, it's been a long time since I've done physics, but uh, we said that okay, you can always assume that the force is coming from here, the center of mass, towards. So, and then if let's say there is a gravity acting on it, then the gravity is actually distributed all across the mass, right? But we used to say that okay, gravity is acting from the center of mass here, and then we used to make these calculations and so on. But even though this force was located somewhere else here, it was still perfectly fine, because as vectors, it's okay. Any kind of addition, I mean, any kind of operations that you do in vectors, it does not matter where you keep it, as long as the direction and the length is respected. Okay. So, but what does it mean? So what does 3, 4 mean? Okay, what does 3, 4 mean? 3, 4 means simply this operation. It means you move 3 steps to the right and 4 steps above. Okay. And this is your 3, 4. This is actually 0.34, but as a vector, okay, this is 3 4. But why did I say that the location does not matter? Okay, it's because take any point. Okay, take, let's say, a point here. Okay, what is this? This is minus 2 comma minus 2. Sorry, minus 2 comma 2. Right, this point. Now let's say you apply a vector there, minus 2 comma 2. So this is a point, okay, minus 2 comma 2 is a point, but I'm writing it in terms of a matrix, okay, 2 comma minus 2, but this is a point. Okay. To this I'm adding the vector 3 4, okay, in order to remove confusion. To this I'm adding the vector 3 4. So what do I get? I get 5 4 minus 2 is 2. 5 comma okay, is something wrong here? Oh, it's minus 2 comma 2, not 2 comma minus 2. Minus 2 comma 2. So minus 2, okay, this becomes minus 2 is 1, 2 plus 4 is 6. Okay, 1 comma 6. Now let's plot that. Okay, so that will be, this is, if this is 1 and 6 is 1, 2, 3, 4, 5, 6. Where do we get it? We'll get it here. So you can see that what has happened actually is I have moved 3 steps to the right and 4 steps above when I applied the vector. So in other words, I have done this. You see that the effect of the vector is still same, because no matter where I apply it, any point I apply it, I'll always get a same displacement in the same direction, no matter what point I choose. So that is the essence of vector. Okay, that is what a vector represents. Okay, just some sort of displacement. What it means by displacement, some distance along with a direction. Okay. Okay, so that's the quick recap that I wanted to do. Now let's just directly jump into the questions. Okay. And by the way, to respect the spirit of the lectures, we are right now focusing only on 2D vectors. Okay, not higher dimension of vectors. Okay. Okay. Can you tell me which of these are correct? So the first says 2 n-dimensional vectors can be multiplied directly, and inner product of 2 vectors is always scalar. If inner product of 2 vectors is 0, then 2 vectors are collinear. For now, forget about D. It's a bit long. So let's look at just ABC. Okay. Okay.
So yeah, so B is correct. Inner product would always be a scalar, and C is correct. The C is not correct, because if the inner product of the two vectors is 0, then it shows that both the vectors are perpendicular.
Which one?
I mean, this
So
is
D seems
incorrect,
to be
that
correct.
D is
Okay.
collinear. And given the two vectors U and V, which are linearly dependent, so one of them, I mean, we should be able to. We can always find any 2D vector W, and which can be written as the linear combination of U and V, I guess, are linearly dependent. I'm not sure, but yes. So D seems to be
So
correct.
by
D seems to be
multiplied
correct.
directly, I mean as
And
matrices.
And the first one, that 2 n-dimensional vectors
As
can be
matrices.
multiplied
Yes, Satendra.
directly. So multiplied, I could not understand. Say, what does it mean? Say U cross V. So if yes, so we can compute, say, U dot V as the mod of U, mod of V, and the
Oh,
cos of
directly. Yeah. So
the
what I
vector.
mean by directly is as matrices. Okay.
Hello, pardon, sir.
As matrix
Hello.
multiplication. Yes, Satinder, what? And so you were
Sir,
saying?
multiplication can be scalar also, and it can be the direction will be perpendicular also. So directly, so I think it is not possible. I think so.
Yeah, that is there. Cross product cannot be done. That's true. And but as nature
Just I
says,
was saying ki,
can you
if the
multiply
two
them?
vectors are there, so their impact will be perpendicular direction also. So in that case, it will be cross product means ki, directly to multiplication will be not possible if the impact is along
Huh.
perpendicular direction of the two vectors.
Huh.
Mhm.
Huh.
Matrices, so two matrices directly it like for if both are of n dimensions, so uh, that also matters ki where will be the
Yeah,
output, I think so,
is
like
matrix
directly to
multiplication valid?
it is not applicable according to me, because it depends
Oh, okay,
that
okay.
where you want the
Yeah,
impact actually, that because matrices also, if we take the cross product, then also it is just like a
okay,
matrix multiplication only, I think so.
okay. Why is it directly not multipliable?
I don't think so it will be there.
Huh.
So I think that two n-dimensional vectors can be multiplied if we multiply
Huh.
one vector with the transpose of the other. So directly not multipliable.
Yeah,
So
yeah,
A is
that's,
not correct.
yeah, yeah. I mean, simply, yeah, that's correct. I mean, simply
So
the
say
fact
if I
that
have a vector, then the dimension
the
of the vector
condition
would
for
be what?
matrix
Say n
multiplication is
cross
not
one.
satisfied. Okay,
And if I have
and
another vector, its dimension would also be n cross one. So to
okay, okay.
multiply,
Uh,
I need to take
so A
the
is
transpose of
not
the
true.
second
So
one, so that its
Goel,
dimension
okay,
becomes one
says
cross
this.
n, and then I can
Satinder,
take
you
the
are fine
product
with
in
this?
similar to the
I
matrix
mean,
way. And
hmm, that's right. That's right. Yeah, that's right. Exactly. A, I have
Yes,
n-dimensional
because
matrices. Okay,
dimension, like if it is
if I have
suppose
two
if I'm writing in
n-dimensional
a
matrices,
column
let's
wise
say one,
vector,
two, three,
like as in the
and
matrix
four,
one,
five,
so
six.
that will be n into
Okay,
one,
so this is
n cross one.
three
Second
cross
will be
one,
m cross one.
and this is also
So
three cross one. But I can't multiply
matrix
this.
multiplication will
Matrix
be not
multiplication is
possible
not
by
well
that
defined
also.
here because the number of columns is different than the number of rows. So they're not defined. So I can't multiply two vectors directly. Okay. So is A is incorrect. Now, inner product of two vectors is always a scalar. Okay. Oh, okay. Yeah, yeah, we'll come to that. Inner product of two vectors is always scalar. I think everyone agrees with this. Okay. So something like 1, 2, 3 inner product with 4, 5, 6 will be just element wise multiplication. Element wise multiplication and add the result. So it's 1 times 4 plus 2 times 5 plus 3 times 6. 6 is 18. So what will this be? 4 plus 10 plus 18, which is equal to um, 20, 32. Is that correct? No? Yeah. So, this is dot product. Okay. And dot product is also sometimes represented like this, okay, with angular brackets between two vectors. And this is a scalar. Now, what is a scalar, by the way? A scalar is a constant, in other words, a number, or in other words, you can also say it is a 1 cross 1 matrix. Okay, I mean, you could also say that, but that's a odd way to say it. But you can always say it is a number. Okay, great. Now, okay. So also, Goel, you were saying that you can do transpose, no? You said that this is allowed. 1, 2, 3 transpose 4, 5, 6. Okay, come later. Like this, 4, 5, 6 transpose. Yeah, yeah.
Not in this way. 1, 2, 3. Yes, 1, 2, 3, and then
Okay.
transpose of 4, 5, 6.
Okay. Let's see.
Let the transpose come
So the
outside.
other
Like
case is
not
1,
in
2,
between.
3. Transpose first, then 4, 5, 6.
Yes, yes, yes.
So
No, sir, it
this
will be
guy will
wrong
be
then.
1,
I
2,
think so.
oops.
1, 2, 3
1, 2
transpose and then 4, 5, 6.
times
It will be there. I
4,
think so.
5, 6.
First
And
transpose into
the
second.
dimension is
Then only it is.
3
Yes, yes, yes.
cross 1, and the dimension here is 1 cross 3. And this is fine. You can multiply them. Now let's see this. This is 1, 2, 3, followed by column 4, 5, 6. And let's see. This is 3, 1 cross 3, and this is 3 cross 1. This is still multiplicable. No? Both are fine. Yeah, I was going to come to that. Exactly. So 1 times 4 plus 2 times 5 plus 3 times 6. This is what you will get. And here also 1 times 4 plus 2 times 5 plus 3 times 6. So, which is nothing but the inner
But then
product.
if you get the transpose in between, this would be the inner
Okay.
product.
So the other
But if you
definition of
put
inner
it
product
outside
is
this, then that would be the cross
U
product, outer product.
transpose V, or equivalently UV transpose. Which one? Okay, okay. Oh, okay, okay. So only the first one. Oh, yeah, yeah, yeah,
Sir,
yeah, yeah.
pardon,
Okay,
sir.
okay,
Sir,
okay. My
that
bad.
second one, I think
This
it is
guy
wrong.
will
It will
be
be 3
on
cross 3
multiplying
matrix, no?
um,
So, second
Yes,
case,
that's
1
the
times
first
first
one.
4
1, 2, 3, and 4, 5, 6
plus.
transpose, that will be not correct, I think. So, it will be 3 cross 3 matrix, it will form. So, that will be no.
So the first column here will multiply here. Okay, okay, yeah, that's right. So this will be a 3 cross 3 matrix. That's
4,
correct. That's correct. That's correct. So this will be 4,
then
5, 6,
5.
8. Okay, okay. So this is
Not
not valid.
then next
This is
second
not
column will
valid.
be 5, and then third column will be 6 in the first row. 4, 5, 6 only, I think.
Transpose of, yeah, that can be done. Transpose of 4, 5, 6 multiplied by 1, 2, 3. So let's see that actually. That's an important point. Let's do that. Okay. Uh,
Uh, we,
transpose of
we can do transpose of 4,
4,
5, 6
5, 6.
multiplied by 1, 2, 3. That will be
Okay.
valid.
Which is
4, 5,
nothing
6.
but row 4, 5, 6 multiplied by 1, 2, 3. Okay. And that is 4 plus 5 to the 10 plus 6 to the 18. So what do we notice? What do we notice? It's still 32. So actually it is commutative in a sense that u, the inner product between u and v is same as the inner product between v and u. Okay. Which is the same as the inner product between. So inner product is commutative. It does not matter in which way you actually multiply. Yeah. That's right. That's right. Okay. So okay. What we get is this is correct. To multiply that is
Yes.
not
So if
correct.
this T
If inner
symbol is
product of
coming
two
in
vectors
between
is
U
zero,
and
then two
V, then
vectors
it
are
is fine.
collinear.
I mean, the other side could be either a U
Okay.
or could be a V. If it is coming inside, then it is a inner
So
product.
I mean, yeah, Satinder. That's right. That's right. I mean, I think you may have seen the formula, right? Cos theta equals u,
So I was
the
saying
inner product
it will be
between
orthogonal,
u and
not
v divided by. Okay,
collinear.
I'll
So
write
that's
it like
why
this.
if
Okay,
inner product is
divided
0
by
means ki both the
the
vectors are
norm of
orthogonal.
u times norm of v, and which means that um, cos theta. Okay. Oh, okay. Which means that Now notice, okay, I'll come to that later, but this guy is always positive. This is always positive. The new denominator is always positive. Okay, so which means that if theta is actually 90-degree, cos theta is 0, which means that the inner product is 0. Okay, and if theta is 1, then cos theta is equal to sorry, not 1, is 1, is 0, theta is 0, then cos theta is 1, then u and v will be what? Equal to the product of the norms. So this is like a litmus test for perpendicularity and collinearity. But what does it say? Okay, so by the way, what is theta and what does theta represent? Well, if you have your graph here and you have one vector here and you have another vector here, see, this is theta. So if you have this, okay, if you have this, you have a 90-degree angle between the two vectors, then this means inner product is 0. Okay, and what does it mean when theta is 0? Well, theta is 0 simply means that both your vectors are on the same line. Okay, both the vectors are on the same line. So this is what this means, and it will be equal to the product of the norms. I'll come to norm, what norm is, and so on. But you see that it's collinear. No? Collinear. The vectors are collinear. Then the product of the inner product of the two vectors cannot be 0, because if it was 0, then it means they are perpendicular. But what we, yeah. Huh.
I have a question here.
Right. See,
So
what dot
now
product
that
does
we are
is,
representing the dot product in
that
terms of
is
the cos
exactly
theta,
what I was coming
and
to.
the
Dot product is a
results into a scalar
representation
value. So what would be the geometric
close
interpretation
to
of taking the dot product of
in
two
the
vectors with them?
close pairs are in direction. Because if so dot product is not like an absolute quantity to represent, okay, but it is an approximation to represent this. That is, if two vectors are completely, I mean, like they have more relation to each other, then dot product is 0. And if two vectors are somewhat, somewhat pointing in the same direction, then what do you have? Then you have that this is positive. Okay, and if two vectors are pointing in the same exact direction, then the dot product is this norm times norm. Okay, and if the two vectors are pointing in two completely different directions, oh, okay, then it's collinear, but it's negative. But if two vectors are like this, if they are what are called obtuse, it's not orthogonal, but it is obtuse. Okay, so this is orthogonal case. Orthogonal simply means perpendicular. Okay, and you have this, then it means that UV is negative. So dot product geometrically measures how closely they are in terms of direction. Note that in terms of direction only. Okay, not in terms of it will be independent in terms of magnitude. Huh. You, because this is also there. No? Okay. Yeah. See. Dot product has various
so
applications,
what
but
could be
geometrically,
the what could be the
we
limit
are
of
only interested with the
cos
positive,
theta?
negative, and
Number one,
zeros.
because just now we saw that the value of the
Okay,
dot product came out to be
you get
32
it?
as well.
Well,
So then, how
okay.
would you interpret that value
So,
of 32
it's
as a
since
dot
it
product?
came 32, it does not for sure mean that
So,
32 is
even if it is
means like it is
there,
closer
then
to
I mean, what
you.
could be the
You only
meaning of the
interpret
value
it in terms of
32
the
when
sign.
the two vectors are close
Of
in
course,
terms of the
the
directions,
magnitude of
but
the dot product is also important in some various applications. Okay, in terms of just the geometric interpretation of it, just the sign is important.
oh, I see. Okay.
Yeah. Yeah, sure. So, dot product, um, I mean, I didn't want to get into it right now because it's not there in the yet in
Yes,
this week's lecture.
so this
Okay.
like in this
So
formula, say
you have
dot
this
product of
concept
u
of
and v is equal
projections.
to the mod of u
Okay.
mod of
So
v
what you
and then
have is
multiplied
you
by
have
the cos
these
theta.
two vectors.
And so
Okay.
basically, what are we
And
computing? Are we taking the product of the
let's say
projection of
something like
v
this,
over the projection of u and
and
then
you want to
multiplied
see
by
what
u?
is
So if you
the
can draw a
the
diagram, I mean,
the projection of this. Okay, here. So dot product represents, okay, that particular value will represent the length of the projection here in the other vector. Well, but and the direction will be sort of represented by the, yeah, Satinder. Huh. Yeah. That's right. I mean, the actual formula of orthogonal projections will have many more things. Okay, I'm not saying that this length is absolutely the
So I
32
was
thing.
saying,
Okay.
like,
Yeah.
we have projected like
It will have
one of the vector
additional
on the
views
second
that,
one.
okay, you need to multiply it by the unit vector to get
So
in the
this
same
will be the only
direction.
the
But I
length
don't
of the
want to
projection.
complicate things. I want to talk
That is
about
not the
what.
dot product, because
Yeah.
this will be the length of the projection then multiplied by the magnitude of the another vector will give
Yeah. Huh.
dot product. So actually, like uh,
Exactly. So the if you look at the, I mean the formula of dot
actually
product, it
we have
appears
the
as
confusion like
a
last time
factor,
also
right? What
we
is
have
the
not
exact
understood. Like if I'm taking the dot product, so whatever the answer is coming, like
yeah
20, 30, whatever it is coming, so actually it is a magnitude part. This much amount will be there. So that much
huh.
amount where it will lie means ki, that part we are I think I'm not understanding that part.
Hmm. Yeah, that's right,
Like excuse me, one more, like
that's
another
right,
one because it has many way to see, like it depends upon that the how you are seeing the things.
that's right.
So according to me, like suppose the first vector coordinate is a1 b1 and the second vector is a2 b2. So directly if I'm going to take the first vector projection on
See,
the x-axis, it will be a1 on the x-axis, projection of one of the vector a1, and now the projection of the another vector will be a2. So both agrees in the same direction.
yeah,
One
see,
agrees a1
okay,
times and
See,
another agrees a2 times.
it's
So their
the
agreement will be
exact
a1
value of
a2
dot product. You
because
will
it will
not
be
find it in the
amplified.
graph.
Means
Okay,
a1
that's
will be
what.
added for the
What you're
a2
simply
times,
saying
something
is
like that. Means the total
you are
resultant
trying to
along the
project it on
x-axis
the
will be a1 a2.
x-axis, and whatever the
Same
value
way
of the vector was
we
a1
project
a2.
along the y-axis.
Okay, you are going
So
to
it will
get
be
a1
b1
here.
b2. So
and this
overall
projection
impact,
you are going
because
to
both
get
are in the
A2 here.
positive
No,
direction, so it
something
is
that.
added. So that part I'm not understanding why we are adding
I mean,
over
if it is
there
A1, A2, then
or
the
something.
projection on the y-axis will be A2. Okay, and this is B1, B2, and the projection on the x-axis will be B2, B1, and on the y-axis will be B2. No,
No, B1, B1 for the even, right.
yeah. So what does it look when you view it from the x-axis? No, so when you are projecting along here, so what you get it on the x-axis is that A1 is like
So
this and B1 is
along
like this.
x-axis they are agreeing A1 B1,
And
A1
when you
B1.
look at
Total
the
this will be I think
y-axis, then you get
amplified
that B1
because
is
one
like
is agreeing
this
A1 times A1 and another
and
is
A1 is like this.
along
No,
B1. So overall impact
until
will
now
be
it is
A1
fine.
B1.
So until
Total
now it
impact
is
along
fine. But
x-axis.
what you are doing in the dot product is that you are doing this A1 B1 plus A2 B2. No, at this point there is a loss of information because now, yeah, the, ah, so
Hmm, 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 hmm. Hmm, 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 hmm.
yeah. I see. The thing is, see, A1 B1 plus A2 B2.
This
There
only
is
I'm
some
not
loss of
understanding ki why
information
we are
happening
doing this
because
part.
once you
Like
have
because
this
geometrically they will form a
value.
triangle, then by
Okay,
cosine
see,
rule,
the problem with this,
ultimately it is
okay, the
coming
why
out to be
you
this
can't
only.
interpret it
But
further geometrically is
some
that
geometrical significance
you
must be there
have
for this
two
part
different
also,
vectors,
because
v1,
somehow it
v2,
must be related,
okay,
because
something
I
like this,
think
and
uh,
some
we have to go
uv,
in depth, then
okay,
only we can come to know that why it is
one moment,
happening so,
there's a person,
something
okay, yeah.
like that.
So then you v1, v2, and then you have this other, one moment, I need to unpin. Okay, good. So now you have this other U1 V2, okay, and he looks somewhat like this, okay, these guys. Now it so happens that V1 V2 is equal to U1 U2. Okay, let's say a dot product of these two pairs happens to be same. Now let's say you do not know what these look like, and this I just tell that what the vectors look like on the graph given the dot product. You cannot distinguish whether the vectors look like this or look like this. Exactly. It's not only the position, actually, you don't know anything about the lengths of those vectors. You don't know anything about the directions of those vectors. You get it? No. There is a loss of information happening, but it's okay. We are just getting some idea from what the dot product actually does. Okay. So, uh,
Because its position is not
uh,
confirmed that there only it is going to lie. It can lie anywhere. Just now you.
right. Hmm.
Hmm, hmm. Okay, sir. Actually, what I was visualizing this part, okay, along x-axis, suppose it is 2 units. So now, suppose one of the vector I projected along
Right.
x-axis, suppose it is 2 units. Now, the second vector, suppose x coordinate is 3. So if I'm going to project, it means that 2 units will be treated as one for the another one. So means that 2 units further will be added. Means that 2 units will be considered as one part, and that will be counted 3 times. That's why I think total impact will be A1 B1. Means 6. One is 2. Like suppose the x coordinate for the first vector is 2. Now that 2 will be treated as 1 unit for that. So if I'm going to project the another one vector on this, so it will count
Satinder,
that
I'm not
2 as a 1
totally.
unit. So now we want 3 units from
See,
this. So that 2 units will be, I think, triplicate. Means कि 2, 2, 2 will be added 3 times, because now we want to move from origin. We want to move 3 units from the origin. So now that 1 unit is 2. So that will be 2 into 3
yeah.
means
No, so
ultimately
what
we'll
I'm
land
saying
on
is
6 on the
I don't
x-axis,
completely
something like that.
understand
I
what
think
you
so.
talked about just now.
That it may be.
The oh, okay,
Actually,
this is 2,3.
we also don't have a clear information that actually what is happening, because we are not a physics student, and what we have been taught in the junior classes
Okay,
or
let's say
maybe in
this is
the
4,3. Just
classes
for the
that
sake of
this is just a formula. What is happening? Never it has been taught actually.
It'll be 2 units. Yeah.
Actually, I'm telling ki, like, let's take the coordinate of the first one as 2 comma 3, blue line 2 comma 3, let's take it.
Yeah.
Okay, and the third one, let's take
Okay.
4 comma 6. No, 4 no, it will be, I think, 4 comma 6, let it be 4 comma 6 somewhere.
0,
So
comma 2 as
if I'm going to
okay.
project the first one
You
along
mean that this is
x-axis,
a 1
it
unit?
will be 2 units. It will be 2 units. Now, from 0 to 2 units will be treated as one
Yeah,
unit,
but why is this
one
a
length. Because
representation
one
of
is
the
in maths, one is not defined. That what is one.
dot product?
Now
Because
for the second vector, if I'm projecting
see,
on the
I would agree
x-axis,
if you
it
are
has to
doing
be
some kind of
it has
division,
to
but you
move
are
4
actually
units from the
multiplying into
origin.
dot product. No, you're doing 2 times 4.
Okay, so I'm not taking this as 4. Now I'm taking this. What is the length? 0 comma 2 as 1. On the x-axis. 1.
Okay, so
So
that
now
is
from
what you
here I have
mean.
to move
Okay, I mean this could be
4
one
steps forward,
interpretation. I agree.
because that was
But
like I'm just visualizing that it may be happening like this. 4. I'm just so this will be treated as for the another vector. This will be treated as one part. Now this part will be moved 4 steps further. So that's why ultimately on the x-axis we land on 8.
see, I'll give a more straightforward explanation. Is that fine? Because see, now once
And
you
same
said
thing is happening
it
along
means
y-axis
now
also.
that
So
this
the
blue
overall
the
impact will
projection
be,
of
that
blue
is
vectors
the
can
maybe some
cover
area of the
4
dot
in
product. So okay, they
cover the
agree
other one
on
in
the one the x,
4 places.
how much they are
Rather than
agreeing on
that,
the x
so
coordinate and how
see
much they are agreeing on the
what
y coordinate
this
after
see why I'm
projecting,
telling you to
and
focus on the
overall impact
direction.
will
Okay,
be
is
what is the
here.
sum overall.
Okay,
So that quantity
let's say this is okay.
I
I'll actually
think may
shrink this
represent
graph.
dot product.
Okay,
One.
and how do I resize this?
Yes sir, yes sir.
Aha, okay. Anyway, let's look at this graph. Okay, and let's see what happens when we project them. Okay, so firstly, let's say these graphs look like this. Um, let's say the first graph looks like this, and the other graph, I mean the other vector, sorry, looks like this. Okay, and you project them. Okay, and you project this guy. Okay, and you project this guy here, and you project this guy here. Okay, okay, they are very close to each other. Okay, they are very close to each other. Then what happens? Well, what do you observe that when you do the product? Okay, when you take this as A and this as B, and this as A and this as B. So sorry, A1, because these were A1, A2 and B1, B2. No? So B1, B2, A2. No? So you get A1, B1 plus B2, A2, B2. thing about it is, okay, A2, B2 is probably very small, and this is very large. This is very large. So, since this is large, okay, it sort of represents that on the x-axis they are very close to each other. The difference is actually very little. Okay, whereas on the y-axis it's very, yeah. Huh. I get what you meant. What you meant is you sort of think about if you take this entire thing as one unit and then multiply it b times, that is exactly your inner product, right?
Ac-
But that is still, I mean, geometrically, how do you
uh, it's like
um,
I'm saying ki
I mean, how
like
do you
we have
draw the lines?
projected
Because like
a1 times
the length of
on the
b,
x-axis. Now a1 times will be added
because
b1 means.
you take this b1 units and then multiply it a1 many times. But what is it
This
representing?
I'm,
Why is it why is it representative of
so
the direction of the two vectors?
so we get uh,
Hmm.
So I so yeah, I have a little issue here that what will be the length of the blue
Right,
line and what will be the length of the red line, number one,
right, right.
and will the product of the blue line and the red line be same as the value a1b1 plus a2b2? So clearly, the value of a1b1 plus a2b2 would be equals to, because there is a relation in between a1b1 this factor and this blue line,
That's right. That's
and I
right.
mean
That's
in
right.
this a1b1
That's right.
some
So yeah,
component
that's
of
that's
the
what
red
I was
line is
coming
there,
to.
some component
Okay.
of the blue line is there.
What I want to
Similarly,
say
in
is that
a2 and b2 some
now
component, I mean
see
components of blue and the red lines are there.
see
So
it
now,
in the
now the
case
point
when they
is
are
that
exactly
a1b1
aligning
plus
with each other.
a2b2 would be
Okay.
same as the product of, I
When
mean
they are
the
exactly
length of the
aligning with
blue
each
line
other.
multiplied by
Okay.
the length of the red line
And
and multiplied
the
by
the
some
the
factor of the angle in
the red
between
one
these two.
also. But see you'll see the
Will
problem soon. Okay.
is this
Now
the interpretation of the
the
equivalence
problem is
of
that
both the
if
things?
I do this and then project it, it's well and good. The value of the product will be maximum. But if I the next factor is agreeing in the direction, but it's not same in the terms of agreeing in direction, but it's not same in terms of magnitude. Okay, this is what we have now. The projection is little. Well, what do we do in this point? Because now the it's not telling me anything, right? If this is a1, okay, and this is a1, this is b1, this is a2, and this is b2, okay, and this is sorry a2, sorry, right? Oh, what am I doing now? B is the second vector. This is b2, this is a2, right? Well, the problem is that so what is the problem? Well, if I do a1 b1 plus a2 b2, what am I going to get? Okay. Now, the fact that they are collinear is going to be the so. For example, if I um, if I look at let's say 1 1, okay, and then I look at another. So let's say this is the vector 1 1, and then there is another point here 1 2 3 4, and 1 2 3. Oh, okay. No, the 1 1 won't be 1 1, and then this will be something like 3 3 or something like that. You know, okay, no, collinear, and 3 3. So 1 1 and 3 3. So if I do 3, okay, times 1 plus 3 times 1, what am I going to get? I'm just going to get their 4 plus 4, which is 8. Okay. Now, Satinder, this is exactly when your idea comes in. Okay, that is the taking it as chunks and then multiplying it to it. What is it simply? Well, what you are actually trying to do is you are trying to take its actual absolute length, okay, and multiplying it with the absolute lengths here. Okay, if they form on the same line. Why? Because this is nothing but the norm of the first vector, and this is nothing but the norm of the second vector. And like you said, if it's asking, like it's saying how many of these do you need to actually form the blue one. Okay, or rather, like if you consider no, not these actually. So if the length of this is something like 8 and this is 3, then how many of these 3s are I mean you are doing this 8 many times. Okay, this is somewhat what is happening behind the lines. Okay, and it so happens that this is equal to, so if you find that so what will be the lengths of each of these vectors? So 3 square 3 square plus 3 square, root of 3 square plus 3 square, okay, plus huh, root 36 is 6, and the other one um, overall result.
Root 36,
What do you
it
mean the
comes out to
overall
be 6
result?
only.
Okay,
Root
so this
18 into
root
root 2. So root 36, root 36 is 6.
yeah. Oh yeah, sorry.
Overall I've
Okay,
calculated.
this is
Like
confusing
first
me actually. 3
3
plus,
and 3 is root
which is
18,
equal to 6.
and 1 is root
So
2.
this is exactly
So root 2
when, I
into
mean,
root 18 is
what
root
you were
36,
talking about
and
happens.
root
Okay,
36 is
Satinder.
6. The overall result will be 6 only. Same thing here.
The issue is when they are
Collinear.
away from each other. Okay, how does it actually react with each other?
See that only
And the
collinear
issue
will be
is
like
also
u
when
into v,
they are
or
perpendicular with each
just now
other.
what we have taken.
Okay,
So I think same.
how does it matter here? And then if you take the projections, okay, of the two vectors, okay, and this is like the x part of the second vector, this is the x part of the next vector, this is the y part of the first vector, and this is the this is the y part of the next vector. Okay, wait, not this one. Now what happens is when it is perpendicular, okay, when it is perpendicular, the projections of the first vector is the second vector is negative, as you can see. For example, in the case of x projections, it is negative. Because of this negative projection, when you compute this difference between the two, okay, that's when you will actually go closer to 0. Now, I mean, it will be useful to actually see how the dot product actually changes when you actually modify the angle between them, right? And the modification is not linear. That is the problem. the modification actually depends on cos theta. That is the problem with representing it geometrically. Because how does cos theta behave? Well, when cos 0, then you have 1 here. And it's not a straight line from here. So it's difficult to represent the change that happens geometrically. The cos theta, when it goes like a wave, right? It's a cosine wave. So it's so to observe the changes as you actually difference the I mean you check at different angles how it behaves. Okay, that is not linear, so you can't represent it directly graphically. That is one problem with this. But what I would say is like play around with these values, like and observe like what happens when these are very close. Two vectors are very close, and what do their projections look like, so that you obtain the dot product as such. Okay, when they are collinear, what happens? When they are perpendicular, what happens? Okay, it so happens that like if the projections on both, so it's like a tug of war between these two guys, the x-axis and the y-axis. Okay, and if this part is overpowering, then the product, I mean it affects the product in such a way that, and if this part is overpowering and this part is not getting overpowered by this particular axis, it's something like a tug of war, then this will have a negative effect on it, and your dot product will be closer to 0, and so on. I would say play around with this and understand like that representing dot products will be a bit tricky here. Okay, and but of course, like the one way to imagine it would be using projections on the x-axis and then finding the difference between them and then adding it up, like it is shown here. Yeah. Okay. Okay. If you have. Okay. Okay.
Sir, one more. We can
Ah.
visualize in the other way also.
Yeah.
That part also geometrically, I'm not getting that part for the dot product concept only.
Uh-huh.
Like if we are taking two vectors, two vectors, we have two coordinates, two vectors. Now that
You mean
what we do
so
if I'm
how
taking the
is
transpose of the
you
another,
mean
means
like the
if I'm
literal
doing the
matrix
linear
transpose?
transformation of one of the vector on the another, so that's so representing dot product. So by exercises, by questions, so it is clear.
Huh.
But what it is doing in actual sense, so from there
1,
also we
2,
can get a little bit idea that
3,
okay,
4.
how that
Okay.
transformation is helping.
Yeah. So it will just sort of flip the
Yes, in the
graphically. Yeah,
matrix
yeah.
form, like
Okay.
suppose if I'm taking one coordinate as 1 comma 2, another I am taking as 3 comma 4. So like two vectors I have got one 1 comma 2 and another is 3 comma 4. Now if I'm finding the, like if I'm if I'm interpreting as a linear transformation means the transpose of the first.
Right.
So if I'm transposing the first one and that matrix means now it
Yeah.
means ki
Oh,
if
okay,
I'm
okay.
multiplying
So
1
what?
comma
Okay. Before that,
3
let's
4 with the
see.
transpose of this means ki
So
actually I'm
what
doing the
is 1
linear
comma 2? 1
transformation,
comma 2 will
something
look
I'm
something like
doing the
this,
linear
right?
transformation of the second vector
Um.
with respect to the first,
Okay.
or
And
I'll do the
3
linear
comma 4.
transformation of the
Okay.
second on the
1 2
first.
3 1 2 3 4 will look
Any
something
we
like
can do.
this.
So
No.
something it is happening. Can we
Okay.
any software is there that we can see that what is happening
Now
if
you take the dot product, but what you are saying is you take 1 2 transpose also, no, separately, and 1 2 transpose will be like 2 comma 1, no, so 2. Ha. So
hmm,
now
now we have to
what
take the
happens
dot
is
product
when
of this
you
by linear.
do this. Okay. Oh, sorry. 1 2. Yeah.
Mm-hmm.
Now
No,
it
1 comma 2. Row wise, it will be
becomes
row wise
a
1 comma.
matrix. Okay, it does not become a column vector anymore, right? So it does not become a column vector anymore.
No, 1 comma 2.
Question is like,
1
but
2,
how do you represent
not 2
this
1.
1 2 graphically? Exactly.
Mhm. So that only I was not getting. Like, so actually, in the linear transformation, this particular
So
thing
so
must be
see,
doing
you are
something with
thinking
the
it in
three
terms
four
of linear
coordinates,
transformation. No.
like three
So
four
what you are saying
coordinates.
is
It
I'm
must be doing
applying
something,
this linear
so that only
transform.
we are
Oh,
getting the
why
exactly
is
the dot product.
one?
So both the scenarios.
So saying
Actually,
that
I was not
you
understanding this part only. Why it is happening?
have this,
What is it, happening? What is the concept behind it?
I don't know why
Something
this is
must be
not working.
happening. So
Okay.
some.
So what you are saying is, if I apply a linear
Yes.
transform of this 1 2 1 3 4, right? What happens here essentially? Now, if you do this, then you get what? So the question is, what do you get here? Okay, will you get a matrix? You won't get a matrix, right? You will get a scalar. Right, exactly. But this is a good question. Actually, I'm okay, yeah. No, this is a good question. So you are saying that since it's converting it to a one-dimensional object,
What we
it
are
should
getting
be
means
doing
we
some
are
kind of
now this
projections
transformation is
on.
converting two dimension into one dimension part.
But how will you plot 1 2 in the graph? That's sorry, this transpose of 1 2.
So, I'm saying कि some tool must be there on the internet or somewhere. Some software will be there. Like we plot the graph, then we see that in the transformation what is happening actually, where it is landing or
That's right.
something it is
It's
happening. If it shows 1 comma 2. No, like sir, transpose of 1 comma 2 means कि actually it is same thing is it happening, like that 1 comma 2 has been transferred into the linear,
but
like
see
two
this
dimension has been
this
converted
this
into one.
1 comma 2.
Like
Okay, so first of all,
actually first
that
we'll
this is
take
this
the
is a
1 unit,
collection of two
means कि on the I
one-dimensional
and
points.
j, both the coordinates मतलब x and
No,
y, both will be represented on the one dimension only.
that one
1
is
and
two
2 both
one.
will be. Now this transformation will be applied on the next coordinate, so that's why we are getting something. I think by picture, by some.
One there is a one and then there is a two. That's what you are saying. No, but where is this one and two located?
Yes, sir, but no. This will be two quantities, like on
So
the number
it could be
line,
located
like
somewhere
0 to
here.
1,
I mean,
and then
it does
second is
not have.
representing 0 to
Uh,
2, means कि we are getting the two readings on the x-axis. Yes, sir. Uh, this 1 comma 2,
See, that's
maybe
it's yeah, it's difficult to represent it because
no,
first you need to decide
it
that,
is no,
well,
now
okay,
it
one
doesn't
comma two is
represents
one
like two
dimension, but
dimension
by
one.
that one dimension, do you mean x
It
or y?
represents now, like I think
Let's say you mean
it has
x.
been transformed to
Okay,
linear
let's say
one,
you
I
mean
think.
x.
Maybe
Okay,
somewhere
then what
it is
happens to
landed
y?
over
Then
the
y can be anything.
on the line or somewhere.
So basically, what
I'm
you'll
not
get is
getting that
this.
actually exact idea.
That is what happens when you visualize a lower dimensional object on a higher dimensional space. Okay, it's like if you are if you
Uh,
look at let's say
hmm.
x equals y. Okay, what does that look like? That looks like this, no? X equals y looks like this. If you But if you visualize it on a 3D plane, you will see that it'll look like this. The plane will look like this. See, I'll show it to you. I'll plot it and show it to you.
Yes, sir.
Register share. Okay. Okay, can you see? Wait, what were they using for GeoChep? Sorry. You can see, right? Hello. Okay. So if you have this, right. So if what I'm saying is, see, this is a 3D plot. Okay, this is not a 2D plot. What happens if you plot x equals y on a line on a 2D plot? It forms a line. But if you do x equals y on a on a 3D plot, the z-axis could have any
Sir,
values.
yes.
This is what it will look like. You get it? So this is the x-axis. So if you look at the plot of x versus y, it will look like this on the two-dimensional thing. But z can have any value here. Okay, z can have any value here. So therefore, it will form a plane. Now, if you unless you insist, okay, wait, this is cannot stop it. Unless you insist that z is something like 0. Okay, but this I can't do here. So all you can do is like z equals 0 plane here. Okay, and then look at its intersection with the other one. Then you'll see that it finally forms a line here. Problem, it's the same problem here. Okay, when plotting, you're trying to plot 1 and 2 as one-dimensional entities here. Okay, but it's a very good question. I need to look into it. What you are talking about. Okay, the current problem that we are facing in plotting what you are talking about is this, that you have two one-dimensional entities. Now, where are you going to place them? What are you going to take it as x? What are you going to take it as y? Hmm. Sorry. Yeah, sir. Yeah.
Sir, that again we are on that question only. Ki like, if I'm doing a transpose of any matrix,
Yeah,
so
good.
actually where it is landing, like matrix, so I'm treating as a coordinate system. So that's why I'm able to visualize. So if I'm doing the
Yeah, but
transpose,
how do you
so
plot it?
that must also represent something. So that only we can understand na, ki, this part is doing something like.
So I guess
Exactly. So, Satinder,
point here that the transpose of
so
a matrix would be the
it's like
reflection of the
when you
values
say
along the
you want to
y=2
transpose
x,
this
isn't
xy
it?
into yx, okay, it becomes a collection of one-dimensional entities. You can't represent it in terms of
For the
points.
matrix,
But
it's
what you
fine.
can do is
I
you
mean, in
can
the case of the
transpose
matrix, in the
matrices,
case
okay,
of
which
proper
are
matrix,
of this form.
yeah.
If you have, let's say, 1001, what does it give you? 1001, what does it give you? It gives you the same thing, right? X comma y. Now what you can do is you can do transpose this 10. Okay, sorry, what happens is x y what? Okay, so this is like one moment. So
X, y equal to x. This will be
one.
just now.
So let's say, okay, this is x y, no? So let's say this is something like, I don't know, 0001. Okay, 0001. Okay, 001. Huh. Yeah, hello.
Sir, sir, can we take in this way?
A B C D X
Instead
Y.
of taking 0,
Then
0 1 1, so can we take in this one form can we take a b c d 2 cross 2 and x y, and that will be equal to x x y, means that will be one dimension,
which
so that
trans
I think it is not possible, I think so, if you are doing like,
yeah. See, yeah. That's okay. That's
is
another good
equal to,
point that you
like, if
made.
I'm
So,
trying
for
to
example, if
just
I want
find
to
that
do,
actually
okay, you are saying
transpose,
this,
which
no,
transformation is working on the
and
transpose of the
the
matrix,
dimension is
this I'm trying to find it out.
2 × 1,
So
and
that
what is
that
the
will be
dimension here?
this will be equal to x
Two
of
cross two. 2 × 1.
yes sir.
Exactly. The yeah, exactly, because when this is
2 cross
exactly
2,
a 2D
another is
point,
2
no,
cross 2,
this is a
2 cross
2D
1,
point,
so that will be 2
and you are applying a transposition matrix here. You
new
should be getting
dimension will
another
be
two-dimensional point,
2
not a
cross 1,
collection of one
so it is
dimension.
not possible, I think, because 1 cross 2, so
But what I
it is
am
not
trying to
possible,
tell
means
you
some
is,
transformation is not working on
instead of
this
trying to
for
transpose
the
points,
transform.
okay, what you want to transpose is the this itself. What is this
Mm-hmm.
called? Transformation matrix itself. Now this is going to make some interesting things. Okay, I mean, this you can actually represent it graphically, and that will be what Goel was talking about. Reflection across X, Y, and so on. Is that clear? I mean, so the transformation of, at least until my knowledge, okay, transformation of vector is a bit weird graphically. It does not completely make sense, because you'll get exactly this. You'll get these lines, okay, and what it represents, that is not clear to me. Is that clear, Satinder? Maybe there maybe you can form a separate coordinate system for that, maybe, but in the same coordinate system it is yeah,
Yes, yes. Means ki maybe some tool is
yeah,
there,
go
or
on.
maybe some coordinate system is there. Like if you try to plot it, that where it is going to land somewhere, so that. Acha. I think maybe some.
uh, uh,
Mhm. Yes, I got it. Means ki, there was lot. Means ki
right,
to
right,
get the depth of this dot product, actually, clear picture.
right, right,
I was not getting. Means ki just to learn that
right.
part. Still, that part also I'm understanding ki why it is A1 B1 plus A2 B2 for the dot product, because
Right,
that
right.
ultimately comes with the cosine of the angle. Because if I'm a vector B vector, and then I'm going to find the resultant of the vector,
Hmm.
and then I'm going to apply the cosine theta formula. So by that, though, ultimately it is coming
Uh.
a1
So,
b1
so I
plus
mean,
a2 b2 is equal to
as far
mod
to
a
my
mod
knowledge
b,
goes, this is
whatever it is,
all that I can tell
cos
you
theta.
about dot
By
products.
that,
Okay,
though,
I
it is
mean,
coming.
graphically,
So
what
that part, though, I was understanding.
if it has a
But
neat
just
graphical characterization also, which can be
I was
easily simply
trying to
understood.
visualize the actually transformation
I
part,
am
what
not
it is
sure
doing.
about that, but
So
if it
I was
exists,
not getting
I'll
the
look it up.
clear
I'll
picture
let you
of
know.
that.
Okay, in the next session, if there is a neat graphical characterization. As far as I understand, it's about how closely these vectors are pointing to the same direction. It's that is all that you can actually understand from it. But if the exact dot product value you
Okay.
can get
Okay.
somewhere in the
Thank you, sir.
graph, it'll be interesting. I'll check it out.
Okay. Okay.
Okay.
Thank you, sir. Thank you.
Yeah. Thank you, sir. Kishore. Yeah. You were raising your hand, Kishore. Hello. Yeah.
Okay, sir. Thank you, sir. Thank you.
Yeah. 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 And even if you plot it, then you get these lines. I mean, because you don't have a y-axis.
See,
Okay, y could be
the
anything.
question for the dot product of
Right.
a vector and its transpose, right? So probably I think it can't be plotted on a coordinate plan of 2D.
Right. Oh, yeah.
Yeah, because once we transpose it, what
No,
we get
you
is
can plot
xy
it,
becomes
Kishore,
fx and
but
then y
it'll just be
just as
that's
xx
why I was
plus
showing
yy.
that demonstration of the plot, no, that 3D plot, because
So,
if you say
which would be a
one
single number,
two,
not a
okay,
point.
and
So if it is
this
not a
is one
point,
two,
then
no,
we can't
so this is nothing
plot it
but
on
the
a
point
coordinate
1 2
plan.
transpose, no. So if you plot this guy 1 2 here, okay, and if you look at 1 2, what does this represent? This represents 2 points actually. Well, Kishore, this represents
No. What I'm saying is transpose can be the transpose of a matrix can be plotted, and it would be same as it
no.
is
I think
as it is.
what
It would
Satinder
be
was
as
asking
of its
was
original vector.
when you
But what
transpose
I'm
a
saying is, as
vector,
per the
what
Satinder's question,
how do you graphically represent it?
the plotting of the resultant of dot
No,
product of its
that
vector
was my
and
point.
its
It won't be same as original. It's a very strange thing graphically, because if you do this, okay, you get this. This is not same as 1 comma 2. This is not same as 1 comma 2. 1 comma 2.
Then it would
Then
be
if it
same
was
as
same, it would be same as saying
original
1 comma
vector.
2 is same as you column vector 1 comma 2 is same as row, right? So what this represents is, okay, it represents two vectors which are one dimensional.
No.
Okay, it represents two one dimensional vectors. Just like a matrix, okay, 1 2 3 4 represented two dimensional vectors, right? So yeah, I know. I know, Satinder. Yeah, you are not saying that they are same. No, I'm telling Kishore that they are not same. You were saying that you were asking what this looks
Actually,
like
I was
graphically.
not saying ki it is the same. I was just saying ki
Yeah.
yeah, it is a form of yes.
Huh.
Hmm. Okay. Some transformation is happening. Like we have been taught just now in the video, like the system of linear equation.
So here
So
that's the
ax
thing.
equal
No?
to
So
b.
geometrically, what
That's
does it
true.
do? If
Ax
you
equal to
plot
b means
this
ki
one and two, it is
a is doing
nothing but
something
x
with the
equals
x. So
one and
that's
x
only we are
equals two,
getting
right?
b.
So
No, that's true.
Because it
this
is
will look like this.
Vector is changing its form, but geometrically it is not changing anything, right?
I mean, these will be the lines when you plot it. So I'm not sure, like because trans like, so that's why this so can this using linear transform. That's why Satinder was saying that I'll what is a matrix M such that when I multiply 1 comma 2 it gets transformed to 1 2. This cannot be done because there is a problem with the dimensions itself. Ah,
So actually we are thinking in the same space. Actually, what is happening?
hmm,
Suppose what is happening?
ah,
Something. What I think so. It must be
right.
happening in this way. Ki, we are
Yeah.
visualizing aeroplane in the suppose like outside in
Yeah.
the sky we are seeing aeroplane. Now the same aeroplane we are seeing on a TV. So both are not same. Actually, in a TV, what we are seeing actually it is in 2D now,
That's right.
and what we are seeing actually that is in 3D. So according
Exactly.
to me, means ki something is happening. Ki this transformation, what
Exactly.
it is doing, it is taking
That's what
the
it
two-dimensional
forms.
space
Yeah,
into
yeah.
one-dimensional
It
space.
forms a, that's
So
yeah,
we
yeah,
can't
yeah.
expect we can't expect we'll get the coordinate. Now we'll get on
Right.
a line. What is the magnitude there? That's why we for the
Exactly.
scalar product
Hmm.
we don't have the directions. What I think so.
Yeah, right.
So
Yeah,
what we are doing, we are searching in the same space.
yeah.
So we are not going to get the any
Huh.
thing over there
Uh,
because
uh,
uh,
Two,
we are
three.
in
Yeah,
the
correct.
another space, one dimensional space.
so one suggestion or one idea what I got just were looking. See, let us suppose vector 2 3 is there and we transpose it. It becomes as a row vector
The
2 3.
original two, three. Yeah, okay, fine. So it will be something.
Okay. So what we can do, how
Okay.
can we plot?
Here,
Can be done is see.
draw a
Can
line
we draw?
segment
We
from
should first
zero
locate the
to
2
two.
3 point.
Oh, okay.
Yeah, on the coordinate plane, and then draw a line
No,
segment from
because
0 to 2 3,
the coordinate plane is showing
from 0
two
0
and
to
three.
2
That's all.
comma
So
3.
so what is it showing? Just one moment.
I
Um.
think that would be the representation on the coordinate plane, right?
Okay. Sorry. Um. So what happens if you plot two, three? You get this blue line, and then you get this three. Okay. But what is two? What is two, three? Two, three is here. So if you see two, three. Okay, this is two, three, and these two lines represent two, three. The it's when you visualize a lower dimensional object on a higher dimensional, yeah, yeah, huh?
Sir, sir, what I'm getting now, like suppose
Hmm.
one side will draw 2D
Hmm.
and one side will draw 1D, like one line, x-axis. Now what is
Hmm.
happening? 2, 3 represents the first coordinate will be 2, like on the same line we'll draw 2 and then we'll move 3. That is for the I part 2
Yeah,
and
you
for the
could look at
J
it
part
that
will
way.
be
Also.
3.
But I mean,
Now
geometrically, you
we'll
cannot
see the
really plot it, no?
whatever the coordinate is there. So it means that
Yeah,
the
we
x
can't
part will
plot.
be added two
I
times
mean, at least in
and the
a
y part
coherent
will
way,
be
you
added three
cannot plot
times
it.
over there.
But it's okay. It's not like a limitation of the thing, but
So it's
you
same
just
space we
have
can't plot
reduced
in
the
this one, I
dimension
think.
when you did a transpose of a single column vector. Now that is interesting. What would be the graphical understanding of
Uh,
transposing a point? I'll check it out once. Okay. Yeah.
Mhm.
Huh.
Okay, sir, like if we get the example of for the physics also, no, so that also will be clear. Like some object
Yeah,
will
but
keep
what?
somewhere in the coordinate plane, and
Huh,
we'll try to apply the
where does the
forces from the
transpose play
different
a role
directions,
there?
and we'll see that where will be the impact. So some diagram, if it is available on net or somewhere. So by
It's
that
okay.
also,
I'll look into it. I'll look into it. So,
not just now,
okay.
next session.
Also, Satendra, that's a.
Okay,
So, I mean,
so
maybe
that also part
I
will,
don't have
I
enough
think,
knowledge about this,
will not get.
but
So maybe, sir.
tomorrow, no, I'm just being honest. See,
Okay,
tomorrow,
okay, sir. Thank
there
you.
is also this
Okay, sir. Thank
live
you.
session with Professor Arun Alan himself. Okay.
No,
So,
sir,
if
you
you
have
join
to. That
that,
that's what we are talking
yeah,
about.
if you join that, then these questions may be very interesting things to raise. Maybe he'll.
Actually, definitely, I'm going to join. But the no, actually, sometimes
No,
we
no,
get
no.
afraid now. So you are very friendly now. If we are talking to the professors or something, so at once they say
Yeah.
that you don't know, that's just silly things, or this is there what things you have studied. So
Hmm.
actually, we get afraid now. Maybe the teacher started scolding, or they will not understand that what actually.
Yeah.
If the child is facing a problem, it means ki definitely something is there.
Huh.
So we can't say because maths is such that ki, we can't say that ki, okay, this happens. Okay, this is the formula, because the person who has written, actually he has not written in a one day. He has studied for I
I
think
mean,
more than 100 years or something,
but
has
see,
been
don't
studied,
be
has been
afraid.
gone
Okay,
on.
he's not going to
Then only
shout
that
at you or
concept comes.
insult you.
So
Definitely not.
how
And
at once it can be
I
understood.
mean, I'm not denying that some people will be there, but I mean, it won't. I mean, at least Professor Arunaran and most professors from say IITs and these research institutions and so on, they will not actually react to that way. In fact, they'll be actually very glad that you raise these kind of points. Okay, so don't be afraid. Yeah, Kishore, you're saying?
Thank you, sir. Thank you.
Okay.
Okay, sir. Thank you.
Just just a quick one. It's not for any like what you say more discussion. See, what you did is 2 3 vector. You
Exactly.
have
Okay.
transposed as a row vector. It is 2 3. Then you have
Huh,
drawn two
huh.
lines.
So
And how you have drawn this on based on what point?
yeah.
Two
Oh, yeah,
three.
yeah. That's right.
You have drawn for two lines. One is blue and one is red.
Sir is taken on the x-axis actually. X-axis 2 coordinate 2, and again on the
Ha,
x-axis
ha, ha.
3
So this will be x equals 2.
and
This
then
will
sir
be
has
x
drawn
equals 3.
perpendicular over there.
Because
So
y could be
that
anything.
then that becomes
Right.
for the blue line the coordinate becomes 2 2,
So if I
and
tell
then for
you
the
in
red
two
line it becomes
dimensions,
3 3.
plot x
3.
equals 2, then it'll look like this. Or x equals 1, it'll look like this. No. Because in two
Yeah.
dimensions, unless you mention this additional equation, x equals 2 and y equals 4, okay, only then can you reduce the dimension and make it 4, because you are actually looking at the intersection between x equals 2 and y equals 4, and it'll be somewhere here. You get it? So if you only give me x equals 2 and no y, but you give me x equals 2 and x equals 3, then I'll get two lines. No?
Oh. Mhm. Yeah, that's of course. But
Right,
see, when we compare from the y-axis,
right,
right?
right.
It is a distance from for the blue line it is 2, and then for the red line it's 3, right? And we are fixing the y coordinate there. So,
We
but
are fixing
we
the
don't have
y.
the
No, we
value for
are not
y,
fixing
right?
the y
Within
value.
that
That's why it
row
was
vector.
forming a line. If we
So
are fixing
here,
the y
based on the
value, then we get a
geometrical representation, we are
point.
fixing the y value.
We don't have a y value. It's missing. I'll give you an analogy. Okay. So so this is like 2 3 6
Okay,
8
okay.
2 1. Okay. What is this, Kishore? This is two three-dimensional vectors, right? This is one vector, this is the other vector. Now, if you reduce the dimension by 1, what do you get? You get
Right.
2, 6, 3, 8. Okay, let's say I ignore this part. Then what do you get? You get two one-dimensional vectors. Is that clear? Right.
Okay.
Now, sorry, two two-dimensional vectors. So, what does this form? This forms a
I
line.
think
No,
it's two-dimensional vectors. It's one
you'll
dimensional.
say okay. You'll say this forms a line, and this forms a plane. That's what you'll say. But okay, now let's try to okay. This forms a line in a 2D plot. This forms a plane in a 3D plot.
Right.
Okay. Now, can you plot a plane in the 2D plot? Not always. Okay. Can you plot a plane in the 2D plot? Not always. Right. I mean, you can plot it, but it will be a very bad approximation. Okay. Can you plot a line on a plane? Well, you'll say you'll be able to plot a line on a plane. How will you do that? Well, you'll say, okay, fine, I have this 3D plot. Okay, you'll say I have this 3D plot, and previously you were saying 262. Let's say this is one plane, and then you were saying 381. Then this is another plane, and so on. Okay, that's what you were saying. But when you say 26, okay, you'll say x 2x, x equals 2 since it's a vector, and y equals 6. No. Oh, okay. I'm sorry. I went to. Okay, it's okay. It's okay. I'll represent. I will interpret it row wise. Sorry. Uh, let's imagine this to be transpose. Sorry. I should have gone one dimensional above. Okay. Anyway, 2 6. Okay. If you want to see it as a line, 2x plus 6y. Okay, because I'm looking at the transpose. Okay, so it will be actually a row. So 2 6 plus 6y, you'll get a line. No, you'll say, but it has a. But what about z? What value of z? You could plot this line here, or you could plot it a bit behind it, or you could plot it a bit behind it, or you could plot it in front of it. Z could be anything. The z axis can take any value. You because yeah.
Can we say Z always be 0?
Hello, sir. Pardon. Sir, I'm saying ki, if you're not, if I'm not going to omit this z coordinate. If I'll keep as it is, and now if I'm going to take the transpose,
but
so
then
it
you've done the
represents,
same
I
thing
think,
again. You've
two
done
dimension. Now
one, two,
the three
and
dimension
you
has
did
been
this, and then
converted
you did a
to two
transpose again.
dimension.
You got back to where you were.
No, no, no. Okay. So that only it means ki this 2D space we have converted to 1D space now. It is just in a single scenario we are seeing this part. Now this
Now
3D, if
see,
I'm doing a
that's the problem I
transpose,
was talking
it
about.
means ki this
If
three
you look at it on a
dimension now
2D
we are
plot, it
mapping to
looks like
two
a
dimension.
one two-dimensional object. But if you look at a 3D plot, it will always form a plane because there are these infinite lines. You get it? Unless you force, like Kishore said. Now, if I add another equation z equals 0, it means I'm
Sir,
adding another plane here, and then intersection will form a line. You get it? No. So these are. Hmm.
No, but when we add Z is equal to 0,
Of course, it does.
does it
I
have
mean,
any such
z
what to
equals
say
0
representation on the
simply means the z
Z
axis
axis?
itself. No,
I don't
z
think
is
so.
0, which means x and y can be anything. So it will be a plane which is exactly containing the z axis,
Right.
parallel to the z
Yeah, that's
axis.
true. Right.
Huh.
So in general terms, what we can say is an
Length and
object
breadth, but any
which
idea,
has
that's a
the
plane.
length and
Yeah.
breadth but doesn't have any height.
Okay. Now,
Can we say
the
that?
thing about lines is lines don't actually exist in the 3D world.
Yeah.
Lines don't exist in the 3D world. Everything are planes, but lines are just intersections of planes. You get what I mean, no? Yeah, Satinder, is that clear?
Yeah. Right.
Huh.
sir, what I was thinking ki like just now what has been written over there, 262 381
Yeah, yeah.
transpose. So if I'm going to take the transpose, it will be 262 row wise and 381.
Two
So
dimension, you're getting
what
3
I'm
points.
visualizing ki in two dimension we are getting 3 points.
In
3 points.
2 dimension, you're representing
I
3
think
points.
transpose
Okay.
may be representing because I don't have the idea for that. Actually, geometrically.
Huh.
So because if I'm taking the transpose, so we are
Huh.
getting 262 row
Oh,
wise,
okay.
and the column wise I'm getting 381. Now it means ki in the two
Yeah.
dimension I'm getting 2
Exactly. Yeah.
3 as a
So what
coordinate,
you're saying is in the
and
3
I
dimension,
think
I have 2
6 8
points.
as a coordinate.
Then on the 2 dimensional, I'll get 2 points, something like that. No. Yeah. That's exactly what is happening. If you completely come up with a new coordinate,
If
the new plot, then you can do it. For example, here you have 1 2, okay, which was a single point here. I'll come up with a new plot which is one dimensional lesser, which is a single number line, and then I'll put a 1 and put a 2. That I can do. That I can do.
On the same line. That only I'm saying on on the same line, like it's just like adding on a number line, like in the junior
Hmm.
classes we write like 8 plus 3, so 8 also represent there only,
That I
and
can
then
do.
3
That I
also
can
we
do. But
represent
you can see that there's
somewhere
a loss of
that
information
part, then we
happening.
have to move forward, something
If
like
I
that.
if you give this graph
Yes sir,
and give
yes sir,
this
that's
point,
true.
I can always tell you that this is 1 2 or 2 3 whatever. Okay, but if you give this graph, I cannot tell whether this used to be 1 2 or 2 1. You see, there's an information loss happening. So what is happening under the
Yes sir,
covers?
yes sir.
I think there is not a neat graphical representation of this. Personally, I think that. I'll check with it and let you guys know. Okay. Okay. Thank you. Okay.
Thank you sir.
Okay.
Thank you
Let's.
sir.
Okay. We are in the first question itself. Okay. Let's look at this one. Given two-dimensional vectors u and v that are linearly dependent, we can always find any two-dimensional vector using two-dimensional vector w using this u plus kv equals w. Is that correct?
No, no, this is not correct. If U and V are linearly dependent, if U and V are linearly independent, then probably we
Okay.
can
Okay.
write
Yeah.
everything as a combination
So
of
I'll
U and V.
just explain this quickly. We have 20 minutes and several questions. um, okay, so let's do this. So if you have u and v that are linearly dependent, okay, which means you can write one vector as a linear combination of the other. What is a linear combination? Well, if sorry, u u1 u2 u3 and so on, okay, are uh, okay, if let's say v u1 u2 are linearly dependent, then you can write v as some alpha 1 u1 plus alpha 2 u2 plus alpha 3 u3 and so on. You can do this, okay, if they are linearly dependent. If they are linearly independent, you cannot do this unless you set everything to 0. Okay, and even this is 0. And additionally, so if you are just given with two vectors, so the only thing you can do is u equals alpha v, right? Because there are no more vectors, and you are saying that they are linearly dependent. Okay. Now, one thing to note that if you do what they are saying is u and v are linearly dependent, and we can always find any 2D vector w using u plus kv. What you are saying is u plus kv equals w is always possible. I mean, for any w is always possible. Now the answer is no. Why? Because okay, let's first look at it algebraically. Okay, so if I put this as alpha v plus kv equals w, then what do you get? You get w equals alpha plus k. So what do you get? W is itself. Not w. Actually, this part. What you get is this resulting vector will also be linearly dependent. And this guarantee is not there, because it would be akin to saying this particular vector is there, v, which is say 1 2, okay, and then I multiply with the something will always give me something like 3 1. Is that possible? It's not possible always for any given. For example, if this was like 2 4, I agree this is possible, but it is not possible if this was 3 1. Oops. I'll give you another reason. Okay, I'll give you another reason, and that is if I have two linearly independent, okay, linearly independent 2D vectors, okay, then linear combination Okay, let's say UV. Then linear combination is something like alpha 1 U plus alpha 2 V. No. Then linear combination, then I can always find a linear combination such that alpha 1 alpha V is W for any W. And this is actually a very interesting thing. So this means that if I have something that are linearly independent, okay, let's say this is 2, 1. So this is U, this is V. Name any point, you can only write that point as this. Why can I do that? Okay. Because of the reason that now you can connect it with the previous lectures, that this actually is somewhat like a system of equations. But anyway, 1, 2, okay, alpha 1 plus alpha 2, 2, 1 is equal to 5, 3. That is what you are actually doing, right? And you are doing, so what is this actually? This is nothing but alpha 1, alpha 2 plus times 1, 2, 2, 1. Is it not? Because alpha will multiply with this guy, okay, and alpha 1, alpha 2 will multiply with this guy. Okay, so I made a small mistake. It should be column vector alpha 1, alpha 2, right? So
it will be not here. It will be transformation of 1 2 2 1 with the column vector column this is alpha 1 alpha 2. This will be reversed.
yeah, this is correct. No.
No. This will be after this one because
Okay.
this will.
Oh, okay. I get what you mean. Let's see. Okay. Alpha 1. Okay. The dimension does not match. That's what you are saying. This is 2 cross 1.
Yes.
Okay. Yeah. Sorry. Good catch. Yeah. So 1, 2, 2, 1, and then so this is 2 cross 2. I want a 2 row object. So alpha 1, alpha 2. This is correct, right? No? Oops.
Yes. No, it's correct.
Okay. And now notice. Okay. So now, okay. Tell me, can I always find this alpha 1, alpha 2?
Yes, we can find.
Why can we always find?
Because either it will be system of linear equation we can solve by Euclidean method or this one reduce Euclidean method, or maybe by A inverse by taking the inverse of that matrix to the other side. So
okay, but okay, for let's say this is not 1 to 2 1. Let's say this is A, okay, and this is alpha, and this is B. Okay, can you always find the value of alpha? Let's say it's some other thing. 1 2 2 1 is just one example, but let's say it could be anything other matrix. Like you said, can I always apply Gaussian elimination?
No, it can it can be parallelized also, so no solution can be possible also.
Exactly. Sometimes I may so happen that maybe no solution, or maybe there are infinite solution. It's possible that that could happen. No, but when can I get a solution? When does solution exist? When does solution exist? When there are multiple ways to say it. One thing is determinant is not equal to 0. The other way to say it is rank is equal to. In this case, rank is equal to 2. But what did we say when rank is equal to 2? We said that the rows are linearly independent. Right. So you get it, no? The column view and row view are actually talking about somewhat the same thing. Here we have row view to actually solve the column view of doing things. So I can solve this, yes, because maybe okay, and because why can I solve this? 1 2 2 1 has rank equal to 2. Okay, you can try this. But so this means that a solution exists. So solution exists. So solve this system to get alpha 1, alpha 2. Okay. So if they are, so now you see that if all the columns are linearly independent, then all the rows will also be linearly independent with each other, because if one is not linearly independent, then it will cause a problem in the other case. The row view, if it's there is linear, this is a problem case. Okay. So I can always solve it. Okay, if they are linearly independent with each other, I can always solve these equations. Okay, and get the fact that I can get alpha 1 and alpha 2, and then I can compute them. So any vector, given two linearly independent vectors, I can always combine them linearly independently and get any other vector. Yes, Satinder.
Sir, just I was saying, ki like we have now this is again the linear transformation of 1 2 and 2 1. If visualize in this form, like x1 x2 is the coordinate, and 5 3 is the coordinate in our original system, like x-axis and y-axis. Like that is the basis. Now that alpha 1 and alpha 2 will be the new coordinate system in the that basis. 1 2
we
and
don't
2,
need
1,
to.
I think so.
We don't need to do
Is
that.
it
We
true?
don't need to change the coordinate system, Satinder, because
Just I'm visualizing ki it is somewhat it is that only part. Ki alpha 1, alpha 2 is the coordinate system for the new basis.
okay.
1 2
So
and 2
that's
1.
one way to interpret it. Okay, that is one way to interpret it. The more standard way to interpret it is, instead of changing the entire coordinate system, you see it as a scaling. Okay. So,
Like it is that ki two different persons are located some different places. So accordingly we are visualizing what we are visualizing from our frame of reference, where means ki where we are standing. What we have observed, that is 5 3. But now the person who is on the coordinate system of 1 2 and 2 1, he is going to visualize at some other place
but that is a very
according
complex way
to him.
to do it, no? Because that's like saying uh, that's like saying if I am zooming
Because
in on a screen, then I am increasing the size of each of the blocks. That's like saying. So
okay.
instead, what I'm saying is, if this is your vector, okay, 2 2. Okay, this is okay. It has a particular length. Let's say its length is something like root 2. Okay. By when you say k times 2 2, okay, if you say k times 2 2, it simply means I'm extending it by a factor of k times root 2 in the same direction. Okay, you get what I mean, Satinder? So
yes, sir, yes,
this process is called scaling. So I agree, what you said is correct. It's like we are increasing the size of these boxes or the grid by a factor of k.
No, actually,
You're saying this. You're saying this. You're saying that I am seeing. I am sort of making this as one unit.
No. I'm not saying that part. I'm saying ki just I'm visualizing as like we are on the coordinate system where we are standing. So we are taking this standard axis as x-axis and y-axis. Now for the other person, maybe its axis will be 1 comma 2 and 2 comma 1 will be the new basis for him.
Okay.
This I'm saying.
Okay.
I'm talking for the basis. Like for our basis is 1 0 and 0 1.
Okay.
And now for the other person, its basis is something.
Yeah. You're correct. Yeah. Sorry, I misinterpreted.
So 5 comma 3.
Okay. So what you're talking about the basis?
Yes, sir. Yes.
That's right. Yeah.
We can think like this. It is some other basis, and he's what will be his coordinate according to the basis.
Agreed.
That will be alpha 1, alpha 2.
Agreed. So that's what That's what.
Is it so? It will be that only alpha 1 and alpha 2 will be the basis for the means will be the coordinate system according to the that person basis whose basis is 1 comma 1 2 and 2 1. I think so.
Right,
Is it
right,
so?
right. So it's like if you have a vector. So I thought you were asking about the scaling. Okay, I thought you were asking that if I have a vector, okay, which is if I have this system, okay, 2 1 2 2 4, okay, 1 2 2 4. Where is 1 2 going? Well, 1 2 is here, no, and 2 4 is where? 2 4 is also
On the same line.
on the same line. Okay, so 1 2 2 4 is not a very good example. I think I need more dimensions to visualize this. But what
Okay,
you actually, yeah, what
we
you
can take 2 1 1 2 and 2 1 we can take. So we'll get the two different bases.
that is true. But I want to represent not that I can reach. I want to represent that I cannot reach everything. But oh, it's okay. Okay, we can do that also. So 1 2 2 1. Because see here you cannot think of changing the coordinate system and so on, because see 1 2 2 1 will be sorry, what am I doing? So 1 2 is here and 2 1 is here. So using this, okay, as so what Satinder is saying, that I consider this as my single step, okay, this as if I'm only allowed these operations. It's like a, in the chessboard there is this knight, the horse. It can only move in certain directions. Similarly, what I'm saying is what you are only allowed to either move one step on the right and two steps above, or two steps on the right and one step above. Can you reach every point using this combination? And the answer is yes, because these two are linearly independent. Okay. Now, if I want to reach, let's say somewhere here, then I can simply do this blue operation. If I hello. 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 Hi, can you hear me? Hello.
I think we lost.
Oh, okay. Yeah, I think that there's some internet repair going on. So yeah, I think that there's some internet repair going on. So that's fine. Okay. Okay. Okay, I should mute. Okay, I should mute. Okay, great. Yeah, sorry. So I can take these as my steps and reach any point in space. So for example, if I want to reach here, then probably I can also move in the opposite direction, by the way. Okay, so probably I can do this operation, and maybe reach here somehow. So can I do this again? Okay, so oh yeah, maybe I'll do two steps here in the negative direction. Then I'll do two steps here, and then I'll do two steps here, and then I'll do this blue step here in the negative direction. Okay. And so on. But you get it. You basically what you're doing is you're sort of changing the coordinate system in order to accommodate this. Now, Satinder, why I was avoiding a linearly independent one. Instead, I wanted to show a linearly dependent one so that there are only particular places where you can land, so that you actually get a feel of what it would be. But that will be more complicated. I think I need more higher dimensions to actually reach that. Okay. But okay, yeah. Anyway, that is what we have here. Okay, I could not cover a lot. Maybe we digressed. Okay. You can hear me, right? Hello. Oh, okay. So I just want to do one quick thing. Okay. I just want to talk about norm. Okay. There are several kinds of norm, but what we want to talk about is Euclidean norm. It follows this formula that if I have two vectors, then if I want to, sorry, not two vectors, what am I saying? If I have, it is also called the length of the vector or the magnitude. What is the effect? It does not, it is independent of the direction. Okay. And so if I want to calculate the norm, I just, if I want to calculate the norm of, let's say 4, 3, I just do square root of 4 square plus 3 square, and then it will come 5.
It will come.
And that will actually correspond to the length of the vector. Okay, this, if you measure it, it will become 5, and it's a simple proof by Pythagoras theorem. This is the hypotenuse, but the good thing is it works in higher dimensions also. Okay, and there are other types of norms also, but Euclidean norm is good enough for what we are working with. But unit vector is all about direction. Unit vector is all about direction. The kind of information it stores is only about direction. That is one neat thing about unit vector. And how do you calculate the, so what is unit vector? Of a vector v, which is represented with this arrow, okay, is a vector of length. Just give me one moment. Okay, sorry. Hello. Hi, Soumya.
Hello.
Yeah, hi,
Hello,
Soumya.
hi, Bhavya. No, I'm in the lab, which I don't have the keys. Like, should I leave it unlocked for a while?
Oh yeah, you can leave it unlocked because yeah, I'll be in the lab in 5-10 minutes. Yeah, it's okay. You can leave it unlocked.
Okay.
I'm here in the department.
Okay.
Okay.
Okay, sure.
Yeah.
Sure.
Okay.
Bye-bye.
Bye. Hi. So what unit vector represents is it is a vector of length 1, and, but same direction. So if I want to find this vector, how do I find it? Well, I compute the unit vector. So the unit vector will be the vector itself divided by the norm of vector. So in this case, it is 4, 3. No, the vector is 4, 3 divided by the norm of 4, 3, which is we got as 5. So we get 4 by 5, 3 by 5. If you plot it, it will exactly be like this. Now, what is the nice thing about unit vector? Well, if you have some other vector, okay, like this, okay, and let's say it's something like 6, 2, okay, I want to shift this vector to this direction, okay, so I want a 6, 2 here. I mean, I want this vector, but in the direction of the first vector. Okay. So now what you can do is you simply multiply 6, 2 by the unit vector. The fact that it has a magnitude 1, okay. Sorry. You simply multiply the norm of the vector. The fact that it has a magnitude 1 will actually work it out. So you do this. Okay, I want to show it visually plotted, but I don't have enough time. So you just do 6, 2. So you find the norm of 6, 2, which is something like square root of 36 plus 4 is 40, times the unit vector, which is 4 by 5, 3 by 5. And the nice thing you will notice is that the unit, you'll get the same length, but in the direction of the original vector. So this is one application of unit vector, and it's used left and right. The main application of unit vector is always to orient a particular vector to a certain direction. Okay, unit vector does not represent magnitude. I mean, it has magnitude 1, but in essence, it represents a direction. Yeah, Satinder.
So I was just visualizing in this way also. Can we think like a unit circle along the
You can do that. Yeah.
unit circle is that circle how it is rotating? Now we'll get the what is the length of one unit along the basis. So in
Yeah.
any direction, what will be the length? Means what will be the radius of the circle, and at that in that part, and what will be the coordinate reading? I think unit circle is giving that part only.
Yeah.
Like it is giving the radius of the circle will be always 1, but because as we keep on moving, so its coordinate will change. Like now it will be not 1 it will be some 0.6 or something like that, because it misses that part, like what unit squares it is missing. It will be somewhat less than the unit square along that part if it is going to move that in a circular way.
Yeah. I mean, that's the if you plot, let's say you plot all the unit vectors possible for that dimension, then it will look like a circle. And if you, it will look like a circle with the basis vectors. I mean, the basis vectors will represent where you can move about even that particular circle. That's right.
So we'll get all the coordinates wherever it is lying, and in which direction we have to move. So suppose we want to move 6 units forward, so we'll multiply by 6 that part.
Exactly. And you'll multiply it by 6 on the to that unit vector. But we wanted to move the length of this green vector many times, the length of this green vector. So we calculate the norm and then multiply it with the unit vector. That's right. Okay. Yeah. Okay. Okay. It's already 8. Okay. It's 7 past 8. So I don't think we have enough time. I wanted to cover quite some things, but it's okay. I'll see next time what to do. Okay. Okay. So okay. I think we can end the session. So any questions?
Thank you, sir. Thank you for cooperation, sir. Thank you.
Oh, okay. Thank you, sir. Yeah.
Okay, sir. Good night, sir.
Okay. Good night. Yeah.
Thank you. Good night. Bye.
Oh, okay. Good night. Okay. We'll meet next week on Tuesday. Okay.
Okay, sir. Thank you, sir.
Yeah.